Okay, guys, we got one last topic to talk about in stereochemistry, and that's this idea that I want to bring up that involves two different new vocabulary words. The vocabulary words are diastereomer and meso compounds, and we'll get to what those mean in just a second. When we talked about stereochemistry before, we introduced the vocabulary word enantiomer. And an enantiomer was a non-superimposable mirror image isomer. And so these other vocabulary words really come to play when we're dealing with molecules that have more than one chiral center. We're going to start off by examining a couple of dimethylcyclohexanes, and we're going to use our new knowledge of stereochemistry to sort out how many actual versions of dimethylcyclohexane there are. Then we'll move in and we'll start to talk a little bit more in-depthly about diastereomers and meso compounds and when that comes into play. And then we'll get into Fischer projections, and we'll talk about why we use Fischer projections and when they're helpful, and how to visualize them. And after that, we'll be done, and that'll be the last bits for stereochemistry, and then it'll be time to move on to thermodynamics. So let's get started. Okay, so before, when we talked about diastereomers, or excuse me, when we talked about enantiomers, we talked about molecules that were mirror image isomers that are not superimposable. And let's take a look at a molecule, and let's give it 3 chiral centers. 1, 2, 3. And I don't actually know what the specifications of this particular molecule are at the moment, but let's just say that there's going to be 3 different possibilities. It could be RRR, SSS. Now, of course, we would have to change the configurations to whatever they might be. It could be RSR. It could be SRS. It could be RRS. It could be SRR. Let's see. I think that's it. Or it could be SSR, because SSR is different than RRS, and it could be RRS. What is that? 2 to the 3 equals 8. Did I get all 8? 1, 3, 4, 5, 6, 7. I got all 8. Okay. So what are the enantiomers? Well, the enantiomers are the mirror image isomers that are non-superimposable. Well, what do you have to be in order to be a mirror image isomer? That means that means every single one of the stereocenters has to be reversed. So there's a pair of enantiomers, there's a pair of enantiomers, there's a pair of enantiomers, and there's a pair of enantiomers. Well, what is the stereochemical relationship between that pair? They're not reversed. So that means they're not actually mirror images. They're non-mirror images. And they're still non-superimposable. Isomers. These are diastereomers. All right, and so let's see, why do we have to think about these? Because at the end of the day, I might give you a question later on in the semester after you've learned a little bit of chemistry that looks like this. Actually, let's use What are the products? Well, you don't know this yet, but the products are this one, and the products are this one. What is the relationship between these two things? Well, where the two chlorines are attached, the stereochemistry is reversed, but where the methyl group is attached, and I'm sorry, if you look really closely, and I make this mistake quite a bit when I'm doing examples out of my head, it's not technically a chiral center. Now I've added an extra methyl, I've added an extra carbon. It is a chiral center now. So back to what I was saying, if you take a look at the chiral centers that involve the chlorines, they have had their configuration switch. If you have look at the configuration where the methyl group is, then you see it's not been switched. So they're not enantiomers. This is a pair of diastereomers. And so ultimately what you're going to have to be able to do with a chemical reaction is not only identify what's the reagent going to do, in other words, add two chlorines, but you also have to say, well, where is it going to add across the double bond? And then you're also going to have to say, what is the configuration that the chlorines are going to add in? Are they both going to be on the same side? Are they going to be on different, are they going to be going different directions? Or is it going to be a combination of both of them? And so in this case, the outcome looks like this. And so it's important to know what the stereochemical outcome is. And they're not enantiomers in this case, they're diastereomers. All right, let's start off with one of my favorite examples that sort of introduces all of these topics. When we first started to talk about cycloalkanes, we looked at some rudimentary stereochemical considerations. We put a cyclohexane up and we then added two methyl groups to it. And we said, okay, is that cis or trans? And what we did is we decided to talk about the location of the methyl groups with respect to each other. And we said, are they on the same side of the cyclohexane or are they on opposite sides? In other words, are they cis or are they trans? And so we came up with the rudimentary stereochemical configuration of cis and trans to identify the one on the top as cis and the one on the bottom as trans. But let's take that a step further and let's examine whether or not using cis and trans is adequate for describing these molecules completely. And so what I do is I draw all four possible projections. Remember, I'm just drawing two-dimensional projections of the molecule. And I want to see, well, what are the possibilities? Are they really four different molecules? Are there only cis and trans like we thought in the beginning? Or is there some other number of real molecules? And so remember, if we're talking about honest to goodness stereoisomers, enantiomers or diastereomers, then they actually are different molecules. But if they are the same configuration, then we find out that that really aren't different molecules. And so what we need to do in order to get this sorted out is to use our ability to specify stereo configurations, and we need to actually assign R and S for the molecules that we have shown. Now, there'll be a lot of patterns that repeat because at the end of the day, the configuration of this one will be the same as the configuration of this one. The configuration of this one will be the same as that one and that one will be the same, and then that one and that one will be the same. So once we start to get a little bit of a hang of it, we'll just be able to say what the stereo configurations of the remaining molecules are. All right, so let's start off with the top left corner, and let's go from there. So what I want to do is I want to look at this particular molecule and these particular groups, and I want to say, is this carbon R or S? Can I sort that out? And so for this particular instance, what I'm going to do is I'm going to draw the hydrogens that are pointing away, because I've got methyl groups pointing towards. And so let's take a look at how I would specify this. Well, I think that everybody would agree that the lowest priority group would be the hydrogen. And I'm going to use blue for the bottom set and red for the top set. So now our job is to point out or assign the priorities of the other groups. It's good that in this case, the hydrogen or the lowest priority group is pointing away from us, because remember, in order to do the stereochemical configuration of R or S, you have to have the hydrogens pointing away from you. That's the rules. And so that's where they start off in this case. And so we're good to go. Now what we need to do is sort out whether or not the other groups, what are the priorities of the other groups? Well, let's take a look. This and this and this are the other atoms that are connected to the chiral center at the top. And they're all carbons. So I need to draw a list to break the tie. And so what I'll do is I'll start off at this location, and I'll write all of the atoms that it's connected to. Well, that's a CH3, so it's connected to only hydrogens. Then I'm going to come over here and do the same thing. That is connected to one other carbon and two hydrogens. It's a CH2 group. And now finally, I'm going to look at this carbon, because that's the carbon that's attached that I haven't assigned yet. What is it connected to? It's connected to two other carbons and a hydrogen. And so now we're able to break the ties with just one list. We see that the hydrogen and the carbon in the first column and the second column, the carbon beats all of the hydrogens in the first column. So this one is now the lower priority. It's going to be priority number 3. And now we can look at the other two. So we know that the middle column is higher priority than the left column, but is it higher priority than the right column? Well, the first one is a tie. So we continue to look at the list of atoms and we find, there's a difference. The hydrogen and the carbon are not the same. The carbon is heavier, and so the column on the right is the higher priority group. Of course, looking down here, we see that there's only hydrogens, so they're tied again as well. So that means that this one is the highest priority of the groups that are tied, and the CH3 group is the lowest. So this makes this one 1 and this one 2. And now that I have them written out, I can go 1, 2, 3, clockwise with the circle that I create. I'm going to erase this because I don't want to get too busy on the molecule, ignoring the fourth location. That circle is an R configuration because it's clockwise, and that low priority group is pointing away from us. All right, let's switch up to blue and let's move on to that other one. Well, we don't really have to do the tie-breaking list because it's going to end up being exactly the same. The groups are exactly the same. So I'm going to have to deal with this carbon, and this carbon, and I'll have the exact same list that I did before. And so this is another bit of pattern recognition. In general, if we're just talking about carbons and hydrogens, the more substituted a carbon is, the higher priority it is compared to one that's less substituted. So this one is going to be priority number 3, this one's going to be priority number 2, and this one's going to be priority number 1. I'll draw the arrow once and then erase it just to show everybody. That's going to be going in the clockwise or the counterclockwise direction. That's an S. So in this molecule above, I have R and S. All right, let's look at the molecule here at the next set at the bottom. I'm going to go ahead and draw out the hydrogens, and I'm going to go ahead and assign them priorities. in this case, at the bottom, I've got the methyl group pointing down rather than pointing up. And so I'm going to have to deal with it in just a little bit of a different fashion. Now, remember, the lowest priority group needs to point away from you, and that's okay for the top carbon, but for the bottom carbon, the lowest priority group is actually pointing towards you. Well, we know a trick for that. We know that that means that we're looking at the molecule backwards. And so that means that whatever arrow that we would draw looking at the molecule backwards is the reverse of the actual arrow we would draw if we were looking at the molecule in the correct orientation. So we'll go ahead and draw the arrow, and then we'll just switch our answer. So again, the priority list should be the same. This methyl group is going to be priority number 3. Priority number 2 is going to be that group, and priority number 1 is going to be this group. So again, drawing the arrow, 1, 2, 3, it's going in the clockwise direction, and so that's an R configuration. And that shouldn't surprise me because this carbon and this carbon look exactly the same as far as their configuration, so they should have the same configuration. Now let's take a look at the bottom carbon. This one is 1, this one is 2, this one is 3, and so I have 1, 2, 3, and ignoring the number 4, I have what appears to be a counterclockwise arrow. But remember, that lower priority group is pointing in the wrong direction. So I have to call that one, instead of going S, based on the arrow, which is counterclockwise, I'll convert it to R, because if I were looking at it in the correct orientation, the arrow would appear to travel in the clockwise direction. So again, remember, this is a trick. It's just a trick to help you not have to reorient the molecule. At the end of the day, the rules state that you have to look at the molecule with the lowest priority group pointing away from it. All right, what about these other molecules? And let's take a look. In this case, I've got a hydrogen that points towards me, and in this case, I've got a hydrogen that points towards me. Now, at the bottom, the bottom one is exactly the same as it was before. We'll come up with the exact same priority list as we did down here. And so we'll come up with the exact same configuration. We'll get an arrow that goes counterclockwise, but we'll say to ourselves that we're looking at it in the wrong direction, and so we will switch this to a clockwise designation of R. Let's double check on this one at the top. This one at the top, I've got the hydrogen pointing towards me and the CH3 pointing away from me. And so let's take a look at how that works. We're going to come up with the same prioritization. So this is 4, this one is 3, this one is 2, and this one is 1. So what I'll end up with is 1, 2, 3, a clockwise arrow. But remember, that clockwise arrow is in the wrong position. I'm looking at it backwards, so I'll call this S. So this one is S, this one is R. That's what's going on with that particular version. So I've got R, S and R, and I've got R and S. All right, so let's take a look at this last one. Let's take a look at this last one. Okay, and so this last one is going to be able to be easily repeated because I've already done the configurations of everything that appears in this molecule. So I've got on the bottom, I've got a hydrogen that points away and the CH3 points towards me. In the top, it's reversed. So in the top, it looks exactly like the molecule above it. And so that means this is going to be an S configuration. In the bottom, it looks exactly like the molecule diagonally from it. And so it's going to have the same configuration as that group over there. And so that's also the S configuration. So what did I end up with? So let's summarize. I ended up with SR here, RS there, RR here, and SS there. So the question that we want to ask ourselves is, well, how many actually different molecules are there? Well, it's going to start to become a little bit more difficult to see, but let's start off with the top row. The top row is where the difficulty starts, and you should start to see this difficulty when you start to think about how would you actually number this molecule? How would you actually describe the position of the R group and the S group? Would you say that this is carbon 1? Or would you say that this is carbon 1? Remember, it actually doesn't matter according to the numbering scheme, because you're going to get 1,2-dimethylcyclohexane either way. So is it 1R2S or is it 1S2R? Really, it depends on how you number it, and there isn't so far a rule to decide that. There is later on more advanced things. There are rules for that, but in this case, we're not going to deal with it. So it should at least give you this conclusion that there's starting to become some problems. And so let's take a look at this one. Well, the first thing that we notice is that it has the reversed configurations. It appears as if there's two different versions of this molecule. It's either RS or SR, depending on how we look at it. But what would this molecule actually look like if we just flipped it over? If we just flipped it over on its side so that this carbon moved over to here and that carbon moved over to there, and everything else flipped over too. What would that look like? Well, if I turns it upside down along this axis, then this carbon, that is the CH3 group that is currently pointing down, would end up pointing towards us. And this CH3 group that is currently pointing down would end up pointing towards us. And so, wait a second, if we just flip it over and we end up with both of the CH3 groups pointing towards us, then what, isn't this molecule really just that molecule? And the answer to the question is, yeah, it is. And what this means, what this does is it brings into consideration one of the last definitions that I haven't actually clearly defined yet. And so it's this. What I want to do is I want to redraw one of these cyclohexanes, but I want to use a Hayworth projection. And a Hayworth projection takes the ring and it sets it on its side so that you can see it in profile. And so the reason why I'm shading these bonds in the front so much more thickly than the bonds in the back is to indicate to you that it in fact does go towards you, and the bonds that are in the back go away from you. And this allows us to project each of these bonds. Now, the bonds in the back and on the sides aren't important. What's important are the bonds in the front. And so why is there actually only one version of the molecule? Well, if I take the CH3s and I put them in the down position, I see that there is actually a plane of symmetry here. And even though the atoms are chiral, yeah, the carbons that are attached to those methyl groups along the cyclohexane ring are chiral. But the fact of the matter is that the molecule itself is not chiral. This plane of symmetry breaks the chirality of the molecule. And this is a meso compound. This is that other vocabulary word that I was talking about. Meso compound. It's a molecule with chiral centers, but is achiral. So it's a molecule that has chiral centers, but is ultimately achiral. That's a meso compound. So let's take a look. If I flipped this molecule over, would I get the same thing? In other words, shouldn't I apply that same logic to the molecules down here? Well, let's see what would happen. Where would the orientation of the groups be if I did this, if I have the same axis and I flipped it over along that axis? Well, this carbon, this CH3 group, would end up pointing up over here on this side. This CH3 group at the top would end up pointing down at this side. And so we end up getting the same projection. And so we would still get R and R. The same thing would be true on the other one. If we come over here and we get flip the molecule over, we'll still get the configuration of S and S. So if we go back and we think about the original question was, with these four pictures, is there one molecule, two molecules? Is cis and trans adequate to describe the molecules, or do we need more? Are there actually four different molecules here? And the answer is, well, no, cis and trans are not adequate to describe the molecules, but there's not four, there's only three. And so what we need to do is describe them separately. And so how would we do that? Well, we've got three different molecules to describe. There's 1R, 2R, 1,2 dimethyl cyclohexane. There's also 1S, 2S, 1,2 dimethyl cyclohexane. And finally, we could say there's cis 1,2 dimethyl cyclohexane. Because in this case, cis does do everything we need to do to describe the stereochemistry. It would certainly be all right to go 1R, 2S, dimethyl cyclohexane. But at the bottom line is that it really does depend on the numbering. And since it's a meso compound, the best descriptor, in my opinion, is to just use cis for this case, because there's only one version of it. And so since there's only one version of it, cis is fine. But there's actually two versions of the trans molecule. And so we do need our specific stereochemical indicators to say which one of the molecules that we're talking about. All right, so this brings in meso compounds. And meso compounds are compounds that have chiral centers in it, but are thus achiral. All right, so the next thing we're going to do is look at Fischer projections. And I built a molecule that looks like this. If you take a look at the inset. Here, let me actually turn off this drawing. So I built a molecule. It looks like this. It's got a bunch of chiral centers in it. So it's got 1, 2, 3, 4 chiral centers. Green is fluorine and white is hydrogen. I got a carboxylic acid group on one side, and I've got a aldehyde group on the other. Ooh, let me finish off my carboxylic acid group. It's incomplete. Oh, well, there we go. Now it's complete. Okay, there we go. Carboxylic acid on this side over here, and aldehyde group over here. And so this is how we would typically represent the molecule, right? With the zigzag chain. And here's all the different chiral centers. There's 4 of them. And so what that does is it provide what the Fischer projection is going to do. It's going to provide an easy way for us to look at the molecule without drawing wedges and dashes. That's really all it's for. Chemists are lazy. We want to come up with lazy ways to do things. And so we come up with these projections to help us look at these molecules and still convey stereochemical information, but without having to draw all the stuff we would normally have to draw. And so let's take a look at that. What is a Fischer projection? Okay. So let's take a look at the Fischer projection. A Fischer projection involves horizontal and vertical lines. On one end of the horizontal line, we put the groups. Here was the carboxylic acid group that I had on one end. That's right there. And then the aldehyde group that I had on the other end. It's right there. Okay. And so then what did I have? I have in between those, I have 4 other carbons. And so we represent them like this. 1, 2, 3, 4. And then the way that I look at it is that I say to myself, bonds that are vertical are coming towards me, and bonds that are horizontal are going away from me. So actually, let me reverse that because I said it incorrectly. Bonds that are vertical are going away from me, and bonds that are horizontal go towards me. So I don't have to draw wedges and dashes. I know that this bond is coming towards, and these bonds, these are going away. The Fischer projection allows us to do this and to have a consistent way of viewing the bonds without drawing wedges and dashes. And so again, horizontal is away, horizontal is towards, I said it wrong again, and vertical is away. The problem is that we sort of started to look at the molecule like this, but the zigzag pattern is a little bit of a problem. So if I want to make sure that the bonds are always pointing away from me, then I actually have to reorient the molecule. And it turns out, in order to get all of the horizontal bonds pointing towards you and all of the vertical bonds pointing away from you, this Fischer projection actually is sort of a false representation of how the molecule is oriented in space. If you take a look at all of these bonds, yes, this bond and this bond point away from you, and these 2 bonds point towards you, but look what I had to do to my pretty zigzag model in order to make that actually the case. So yes, the Fischer projection helps us see the stereochemical consideration of the molecule, but it doesn't allow us to do it with any sort of realistic projection of the molecule. So you have to keep in mind that it's not ever really going to be in this position represented by the Fischer projection, but we can still see it. And so if I were to look at it from the carboxylic acid side, I would see that I've got fluorine, hydrogen, fluorine. And so that means, let me back up. Hydrogen here, hydrogen here, hydrogen here, hydrogen here, and finally the fluorine here. And so they do have, now that you've done this projection, you can specify all the stereocenters. And so what I want to do is I want to show you an example of specifying 2 of the stereocenters with the Fischer projection set up the way it is. And that way you'll see that you can use this to specify the stereo configurations. And so what's fluorine? Fluorine's got a much higher, or it's not much higher, but it's higher than hydrogen. It's higher than carbon. So it's going to be the #1 priority group. The hydrogen is the #4 priority group because it's the least massive. So let's take a look at this carbon and this carbon. Well, remember that both of these carbons are tied. So we have to draw a list to break that tie. Well, the carbon below is connected to a carbon. Let's do it in order. Hydrogen, carbon, and fluorine. And the carbon above is connected to oxygen, oxygen, oxygen. Well, yes, hydrogen beats oxygen. Yes, carbon beats oxygen, but fluorine beats oxygen. And so because this carbon, the fluorine is larger than the oxygen, this is the next highest priority. This is priority number 2, and this one would be priority number 3. Now, of course, that consideration may change as you move further down the line. So let's take a look. All right. So now that I've assigned this, I've got the arrow that goes 1, 2, 3 around the circle this way. Well, that's a clockwise circle, but keep in mind that horizontal bonds go towards you. And so that hydrogen, the lowest priority group, isn't correctly oriented. So we have to use one of our tricks. And the trick would tell us that if we have a clockwise arrow, we need to reverse it. So this is an actual configuration that is S. What about let's do the one at the very bottom. Let's do this carbon. Well, I've got fluorine is the number 1 group. Hydrogen is the number 4 group. I've got this carbon and this carbon to deal with. And I'll actually end up with the exact same list. So that means that I know that this is carbon number 3. Actually, it's not the exact same list. It's just a little bit different. There's a hydrogen there instead of an oxygen. But I'll still, at the end of the day, get hydrogen, carbon, and fluorine for the other list. So that means that the carbon above it is the next highest priority, number 2. So if I use my arrow, 1, 2, 3, I get a clockwise arrow. But remember, it's not going, the hydrogen is pointing towards you, not away. So that clockwise arrow should be specified as, oh, you know what? That's not a clockwise arrow. That's a counterclockwise arrow. So yes, it looks like an arrow for S. It's actually an R. Let me just double check up here. 1, 2, 3. That one actually is clockwise, so it really is an S. All right, so that's how you use those projections to specify stereo configurations. Well, what else is good about them? Well, what else is good about them is that I can easily draw enantiomers. Well, how would I draw the enantiomer of this molecule? Well, if I have this here and this here, and I want to draw the enantiomer, then what do I have to do with each stereo configuration? I have to reverse it. Each stereo configuration has to be reversed in order for it to be a mirror image. Well, what is that other trick about reversing stereocenters? If I swap the positions of any 2 groups, then I've reversed the stereocenter. So all I have to do is draw F here, H here, F here, H here, H here, F here, H here, and oh, didn't reverse it. F here and H here, and now I have the enantiomer. Okay, great. What else can I do? Now that I've drawn the enantiomer, I can also draw a diastereomer. If I change the position of just 1 or just 2 or just 3, but not all of the stereocenters, then they're not all reversed. So it's no longer a mirror image. Since it's no longer a mirror image, it's a non-superimposable, non-mirror image isomer. So these are diastereomers. All right, there's one last thing that I want to talk about before we wrap up this bit about stereochemistry for good. Now that I've got this Fischer projection out, I've kind of talked about what it's good for, what its limitations are. We've talked about how to use it and still specify stereocenters. We talked about how easy it is to draw enantiomers and diastereomers using it. The other thing it's pretty good for is identifying meso compounds. Now, I have to change the molecule. Instead of OH at that location, what if it's another aldehyde group, just like the one below? Can I arrange these groups here so that it's actually a meso compound? Well, yeah, remember, as long as there's a plane of symmetry, then that means that the molecule is actually achiral in and of itself. And so here's an example of a situation where there would be a plane of symmetry. Everything above the plane is the same as everything below the plane. So this molecule is actually not a well, it is a diastereomer, but in addition to being a diastereomer, it's also a meso compound. It's not a diastereomer of that, because remember I changed this group, so it's not even the same molecule. But diastereomers, but it is a meso compound because of the plane of symmetry. And so Fischer projections also sort of are good at helping us immediately see planes of symmetry. Okay, there are other topics in stereochemistry that I'm not going to discuss that I don't think are appropriate for this particular course. We could take Fischer projections and talk about the biochemistry of sugars and really get a feel for the different types of sugars, because it turns out that if we start replacing fluorines with OH groups, then we really are kind of talking about sugars at this point. And whether or not the configurations are left, or excuse me, are R or S, is one of the things that separates sugars from one sugar from another sugar. And so I'm going to leave it right there and sign off. If you have any questions, you know how to get a hold of me. Hope this helps.